It's true.
Sweet. There's a cowboy hat, man. You have a hat?
Ready? Okay, great. Our next talk is Off-the-Shelf Security, Meeting Crime with an Open Mind by Nick Waite, Bert Cates, and Stephen Janansky.
And of course, and crew.
And crew.
Right.
Actually, the crew is kind of the point of this project because I'd been working on some of the core hardware for this for a long time ahead before that, just for my own purposes. And thanks to the enthusiasm of Mr. Janansky here and Fuad, the professor at our university who sponsored the project to be an actual undergraduate class, the little hardware I'd been working on and the wireless router expertise that Steve had been building up got turned into something that actually got to see the light of day here. So got to thank everyone for that. Well, I guess we are the circuit breakers. We are a newly formed hackerspace. We'll see what it becomes. Just started this semester really, but everyone came back from DEF CON fired up and thought this would be really fun to do more of regularly. These are the crew. Are you guys in order?
No. Not at all. No.
Oh well. I reckon that I'll just say the name. Raise your hand. Alex, Burke, right? Josh, Lawrence. All right, right. Mike, me, Rob, excellent, and Steve. So, yes, I guess I've noticed in recent talks this tendency for more and more projects to be built with wireless routers. Somewhere along the line, either intentionally or unintentionally, this emergent sort of thing is coming up where people are realizing wireless routers are great. They're fast, they're smart, they have built-in communications for everything you could possibly want. They're cheap. Linux runs on them. You can put stuff on them. They're great for everything. Why? You could even run a UAV with them. So lots of people out there who want to build hardware have projects that need brains and comm like that, and wireless router provides a great solution. Problem with them is, of course, they're not built to actually control stuff. They're built to route packets. So, you know, you have maybe 4 GPIOs, which are linked to LEDs and switches. You will burn a huge amount of CPU time doing bit banging on them, and I haven't heard if anyone's managed to put a real-time kernel on those things to make interrupt-driven bit banging I/O possible. So you may have a 100 or 200 megahertz processor, but you spend a great deal of its time just sitting around waiting for something. That's not cool. And of course, you may need to burn 3 watts or more to keep them running, which is also not cool. The solution for this problem is, you know, like the Open Vulture guys did, you have a microcontroller that serves as sort of port expander and real-time extension. So you can have the microcontroller running some code that actually is designed to respond to real-time events very quickly without burdening the router, or even shut down the router with some kind of a power switch and wake it up. This is kind of like having a reptile forebrain and then some kind of a cerebral cortex that's slower but more sophisticated. So this is what my original system was designed to do, which was related to weather sensing and relaying it. Originally, the plan was to use a microcontroller to turn on a router, and the router did most of the intelligent stuff and sent up stuff by Wi-Fi to some central location and stored it. And the microcontroller was mostly just a port expander, and that actually worked quite well, but it was very hungry for power, and there's no way to make that really work well. So this was based on a PEC, and this is our really, really ghetto setup. I have to thank the guys who made Hacking the 54GL for their fine book, because that made life very easy. Build experience on that. The next version of the sensor board that we built was also a PIC, but it was an actual board, not some little prototype board, and it had the SD card built on. It was designed to mate with a fawn. So if you look at it, you can actually see that the Phanera, where the Phanera has a jack, there's a mating jack, and where the GPIOs are, there's also a mate. So the SD card thing, the SD card mod that OpenWRT has, is supported there. So actually what that board did, which was kind of interesting, was you can see near the blue power input, there's actually a MOSFET there. So part of the solution there was if we have a battery, we can actually have the microcontroller with a real-time clock running on it, power down the router when it's not needed, wait until some time clock elapses, then actually turn the power back onto the router. So you have this ping-ponging of control back and forth. The router tells the microcontroller when to wake it up, and then the microcontroller puts it to sleep and wakes it up at the commanded hour so that it can do what it has to do, or in response to certain signals. This was not ideal, but it was a lot better. So the alpha version, this is another side view of it, actually with sensors attached, and that's the lovely little fawn there. You can see the red wires on the left side jump up to the GPIO pins, and the fawn header there with the really ghetto wire wrap tri-row socket being used as a double row socket gives the jump down, but it worked quite well. We needed something better though, and the solution was to actually go to a type of processor that our university uses for the Introduction to Microcontrollers project, which is a class, which is it's kind of an old school 8-bit microcontroller, the HCS08. It's pretty fast, maybe 20 megahertz. It's showing its age a little bit. Certain things like the real-time clock are kind of clunky and hard to use, but it's actually pretty big. It's got 60K of flash, which is very large in the 8-bit microcontroller world. So it gives the ability to do lots of complex things, like having a FAT16 driver. And we actually ripped from the DEF CON badge some code which Kingpin adapted from some Freescale code. It was a FAT16 driver, an SD card driver, and actually I've ripped out and repaired probably 30% of it. Some things like how it initializes the SD card is kind of questionable, which goes to show that you shouldn't really trust the makers of microcontrollers when they give you free code. Beware of geeks bearing gifts and all that sort of thing. So this one, in order to get the power conversion done, the fawn or the thing which is not present on this board here, which would fit in the headers around that microcontroller, maybe you can see it up there, that would be an XB, which you probably know, I suspect from Travis Goodspeed, is a little standalone module that makes Zigbee or 802.14 behave as though it's a virtual serial port. So it's a really nice, easy bolt-on sort of thing. And actually in our testing using these things with the version of the XB that has an external connector, an RPSMA connector, rather than the onboard little wire, we were able to achieve, I think, what was it, 1,000 feet?
Just over.
Yeah, maybe 1,400 feet line of sight while still having connection between them using little tiny, just the normal Phanera or Wi-Fi, maybe 4-inch high rubber ducky antennas. So they're pretty intense. They'd actually be pretty good for control of like an RC aircraft or something. I think far better than Wi-Fi unless you had to transport video or some high bit rate thing. And if you were to use them in API mode and actually pack the frames up carefully and send them out rather than using the virtual serial port's default behavior, you could do it even better. The point is that when you run off a battery or something, you may not have 3.3 volts though. So on board there, you can see up under 3.3 volt power converter, I used a little power conversion module from TI in lieu of actually constructing that thing myself because of time constraints, which it provides 3.3 volts, I think up to an amp or so, maybe even 2 amps, at what they claim is 90% efficiency. Later I found out it turns out that's true, but only at 50 or 60% load. At low loads, it pulls like a constant 20 milliamps from whatever power supply you've got. If that's a 12-volt battery, it's pretty ugly. So that's going to have to get ripped out and replaced with something better later, for those who care. This is the final version of the board, which was soldered together not too long ago. It's actually nice and green. It's got solder mask and silk screen, and most of the bugs in the board have been patched. But the same sort of format exists as the old board had. You have an input power thing. There's actually reverse current protection in the MOSFETs so that you can't back the battery in the wrong way and blow something up. There's the power switch, the power converter. It can actually still operate the FON, the header for the FON RS-232 and power, as well as the GPIO pins are still there. And you may have noticed that there's now a programming header on the board. I had quite an entertaining time with the prototype boards when I realized they didn't come with a bootloader on them. We had to do some crazy trace cutting on the FON header. So this is, I guess, a very basic wireless mote now, or it will be. If we eventually integrate the Zigbee and the power converter on board, it could actually become something quite cute. For now, it does the job. The SD card driver works. The FON works. The power converter works, albeit inefficiently, except when the XB is in actually transmit mode. And it forms the basis for a much larger system which we've been developing, that these guys all around here built extensions and parts of. So my job, I guess I should be clear, my job was to provide this platform, but not to constrain what they did with it. And I'm kind of happy to see what came out of it in the end. So that was this is just what it does, I suppose. It can do whatever you want it to do, like most machines can, but I'm actually thinking of making an engine controller with it. It would be quite nice to use as an ODB1 or ODB2 data logger for a car. You put a 2 gig flash card on there, you know, you can do a lot of stuff with that. But that's for another time. For those who aren't familiar with this kind of hardware, microcontrollers have a bunch of advantages. Like, you can't run Skynet on them. They're a little too small. So when the machines come, at least our microcontrollers will be safe, we think. But you can see that the wireless router and the microcontroller actually complement each other quite well. And their price is both small. So I would say that probably we're going to see a whole bunch of talks in the future about hunter-killer droids, UAVs, remote access vending machines, RAID array toasters, whatever, that operate with this combination of things. And I guess I'm hoping that the end result of the class, after we are done here and we clean up our code, will be something we can post up that'll make the job of integrating the wireless router and the microcontroller side with each other easier for all those people out there with projects they'd like to get going without having to hack together a complete system. So I guess, do I transfer over to you now?
No, you get this
No?
slide.
All right. Well, so, yeah, the grand scheme of it all, to save you waiting for the complete end of the presentation and to keep in your mind and turn around, is that free open source software plus a router plus some custom digital glue gives you the power to make pretty much everything that I can think of. So this reminds me a little bit of the time when first computer processors became on the market, like when the Apple II came out. Before that time, you could make a computer, but you'd pay dearly to do it, even if you built it yourself. After that, it was still rare to find one, but it wasn't expensive. It just required skill. And as things became more common, more and more people with less specialized skills could find out what the computer could do for them. And I think this may be maybe not as important, but a new time for hardware hacking, because enough processing power and hardware is available cheap enough now that pretty much anyone can buy what you need, slap it together, and make something pretty impressive. Live video feeds, robotic control, pretty much anything. So I can't wait to see what the result of that is. And I'll hand it over to my colleague here, who will take it away.
All right, thanks, Nick. So like Nick gave you an idea, the whole idea of this was, while we're doing all this, why not just do it right and do it so that we can then release it so that everyone else can use it also. So keeping that in mind, it's one of the things we did. So like when we went to link the microcontroller to the actual router, we decided to use Perl and also Python. We tried both, so scripts have been written in both languages to allow you to pull the data from the microcontroller onto the router and then upload it to the internet via TCP or UDP, however you feel. then what we did was we defined an opcode-like structure, which just allows you to optimize IDing sensors and other things like that. And really, protocols was outside our realm, so we just tried to give it the best we had. So here's the idea. This is where the rest of the group came in. The idea was, let's take everything that we had from Nick and what I had done, and let's make the system on its own and give the guys a chance to do what they want with it. So like I said, we added the I/O support. We wanted to add I/O support for other devices, and we wanted to make sure that the software was easier for everyone to interface to, which is why we standardized what we were using. But most importantly, we kept using these open source projects because, quite frankly, I can't code well. So we decided to take what other people had done. So thus enters the circuit breakers. We gave them the base platform. We asked them to design a project. And as you may have guessed from the title, they decided to do it on security. Now, a quick blurb about why security. We're from the University of Delaware, and in the past fall, there were several attacks that occurred around our campus, and as time increased, they got closer and closer into campus until they started occurring on campus. So it was just a heated subject at the time when we were brainstorming, and so we thought, let's give it a shot, and also, you know, it could benefit some people for a home security system. So thus, what we call the Death March to Shmoocon began January 2nd. We had the base system, what Nick described, up before then, and then everything from this point was done by these guys after January 2nd.
What was the nature of the attacks?
The natures of, they were usually muggings and robbings, but usually occurring in areas that were, how do we say, dimly lit, but also very ill-patrolled, we'll say. So the idea was the police force was limited. How do you prioritize where they patrol, things like that? Does that answer the question?
Actually, I want to add, the general idea here was that adding more sensors doesn't make security better. It gives you more monitors to watch. That's not really a solution at all. So the idea here was that if you made a sensor system that was simple-minded and therefore easy to build, but had multiple layers of inference and filtering on it, very simple sort of things, but you know, if you hear a loud noise during Friday night, it's probably not a problem, unless you're away from the bars. If you hear a loud noise during Sunday night at 1 a.m. or 2 a.m., it may be much more something to be concerned about. So simple inferencing and that sort of thing, the idea was actually not even to detect crime. The idea was to detect interesting things and prioritize video feeds to people who have to watch monitors so they don't spend all their time watching monitors with nothing on them. I think there's been a lot of talk about sensor fusion and sort of artificial intelligence, and I don't think for most interesting applications, since the problem is human, the solution can be anything other than human. But just by detecting conditions that are conducive to crime, and using that to rearrange the priority of patrols and that sort of thing could actually create a very much enhanced security. I don't think Big Brother is the idea at all. It's more like an organic system. When things feel freaky, you change stuff up a bit. And thus, criminal patterns may have a harder time developing in the first place. That was a general idea. It also has the nice byproduct that what we write doesn't have to actually work all that well. It just has to, in aggregate, prioritize feeds of data it just has to prioritize feeds of data in such a way that the people whose job it is to keep you safe actually are watching stuff where they might have some value. So that was the system.
That's better than I could have said. So here's the base requirements we set for the hardware of the system was we wanted Wi-Fi. The campus around us had lots of Wi-Fi. We're upgraded the G, full coverage area, so we could take advantage of that, so we could deploy these sensors in the field. We wanted USB 2.0 to give us the ability that if we needed additional storage, but more importantly, USB peripherals, as you'll see, were added. This included a USB webcam. Then, most importantly, to communicate with the microcontroller was going to be the serial communication. And we wanted the router to support OpenWRT so that we wouldn't have to go code all that firmware for the router. So thus, our fight with the routers began. So round one was we found this nice router made by ASUS, the WL520GU. It came out, it was about 50 bucks, and then you could get a rebate on it for 30, so that brought the price down to about 20. It has a Broadcom chip, which for anyone that knows OpenWRT, Broadcom has, initially was the first that was kind of gotten into, but now it seems to be stalling out as people are stuck on the proprietary drivers, but that's being dealt with. We want to submit this for the contender for the worst UI ever because it was just, you logged onto their interface, it was purple and green and did absolutely nothing and threw JavaScript errors every other page, so just horrible. It was listed as a work in progress by OpenWRT, meaning that people had gotten it on, but as you'll see, there were some troubles with it. But the only trouble that we saw ahead of time was it only had 4 megs of flash, which limited our abilities. So sadly, this router won out. The deal is, you want USB 2 support? That's only in 2.6 version of the Linux kernel. You want the wireless module that works for Broadcom? Only in 2.4. Now there's a reverse engineering going on called B43, or used to be BCM43. However, they don't support it because it has this thing known as an LP-PHY, which we're guessing meant it's a low power and has an amp on it, but hopefully they'll be resolving that soon. So thus, we concluded that this was a failure and moved on, and as you can see, Grungy was not happy about this at all. So thus, we moved on to this wonderful new thing called the Ubiquiti Router Station. Now, for those that don't know, Ubiquiti is based out of California, and they design custom hardware for routers and other things like that for giving coverage area. And they advertised this new great product called the Router Station. And it was supposed to come preloaded with Kamikaze and 2.6 of the Linux kernel. You could add mini PCI cards, which meant you could add cards that were supported by OpenWRT. And it was extremely powerful. I think it boasts something like a 680 megahertz CPU when the average nowadays is just under 200 megahertz.
Not to mention 64 megs of RAM
and
16 megs of flash.
64 megs of RAM and 16 megs of flash compared to the 4 megs of RAM and 8 megs of flash, or 4 megs of flash and 8 megs of RAM that we just had on the previous one. The problem was the device shipped, I think, something like January 21st. So as you know, we're here on February, so we didn't have a lot of time with it. It didn't ship with a power supply. What they wanted you to do was power it over Ethernet so that you could use an injector on it. But for us, that just kind of made it a nuisance at first, so it was a slight annoying. And when they said it was OEM, they literally meant initially it was OEM. And now the Ubiquiti people are kind of changing their mindset. They're putting more documentation up on the forums. But if you go look at those dates, there are a lot that's occurred within the last week. So we were literally poking at this thing. And we're getting a lot of weirdness with the USB. Sometimes the thing just turns off. It doesn't. We've tried external power sources. So not sure what's there. We're in talks with their tech support. But most important, it was costly, both in power, as you can see, but also it sells for about $70 retail. Plus, you've got to get the wireless card. So now you're talking close to $100, and you don't even have any sensors. So seems like a cool idea for anyone that wants a really powerful home router, but for our purposes, we had to move on.
Not hunter killer. Just keep that on the shelf when the documentation gets better.
Yeah, it's going to be really nice once they get that fixed. So thus, our third try was with the new Fawn that's come out, the Fawn 2 beta, which is shipping for developers right now. They're trying to get people to code on it, to get working on it. And the thing that it touts is this USB port, which is what not a lot of routers had, and we really wanted. So when we saw that, it screamed at us. Has the same system on chip as previous versions, and as you can see, we were using Fawns before, so I already had a lot of pre-written code for it. And most importantly, it supported that 2.6 kernel with both wireless and USB. So basically, we declared victory over this one. It met all our goals. On top of that, we had the benefit that it was small and compact. It was cheap for us, and it ended up being a great solution. So now I'm going to turn it over to one of the guys who actually worked on the microcontroller side of the project. Rob, where are you at? All right, Rob Hayslip, everybody.
Thanks, Steve. We also got Mike Nathan coming up here with me. So basically I'm just, this is just a slide about the HCSO8. Again, it's a great platform for all our sensors that we used. And so we're just going to go through a couple of the sensors. The first one was the passive IR sensor, and Mike's going to tell you a little bit about that.
Hi. This passive infrared sensor, it only costs about $10 at Radio Shack. It has a 3-pin connection, so it has a digital output signal. When you turn it on, how it works is it detects the environment. It takes about 30 seconds to warm up. And once it has that environment in its system, when it detects a change in that environment, if anybody moves or anything like that, it sends a signal. So this signal got sent to the microcontroller, and from there we used that with a keyboard interrupt, which was able to turn the microcontroller from low power mode to high power mode, saving power. And we turned on the other sensors when that happened.
For those who are interested, this sensor is made by Parallax, and you can pick it up pretty cheap. I think $10.
$10.
So at this point, we're going to start talking about how you could actually build the security system. Just forgot to include that slide, so sorry about that.
Sorry. All right, so here's a good picture of what we had in mind for a test environment, for an environment where we would implement our project. So you can see this is, well, it's during the day, but it doesn't look that sketchy right now, but you can imagine. So on the bottom left of the slide, you can see there's the passive infrared sensor Mike was just talking about. And so what would happen is, if you can imagine the person walking by just from the bottom of the slide to the top, that you can see first tripping the passive infrared, then the tripwires would go off, and that would tell you the velocity and the direction, and the speed, which is speed and direction, at which a person was walking by. So if you had, a person that was innocently walking home from working hard on an engineering project late at night, and then, of course, a mugger comes by and runs and sprints right at him, they're first going to trigger the PIR, then the tripwires are going to go, and then we're going to have the audio sensor go off. And so you can see how all the sensors work together like that. And I'm sure we'll go into more detail with the other sensors later with Alex. So yeah, but I just want to talk about how we work the power system for the PIR and the trip sensor. And Mike's going to tell you about that.
So as you can see on this slide, there's 2 sets of every sensor. So in the system that we're thinking of, we would have 2 different boards and 2 different setups. So on the first board, we're going to have it plugged into the wireless router, so that'll be powered. The second board will be battery powered, so we'll need to worry about power consumption and saving the battery life. So the reason we used the passive infrared sensor to go into low power mode was for this reason, to save the battery life. So in running mode, it uses about 50 milliwatts, and in low power mode, it only uses 120 microwatts. So that's saving about 400 times the battery life. So with the second one running on the battery power, it's using Zigbee communication, so saving that battery life lengthens the time that we can use that same sensor.
What was the total consumption for the entire system compared to these numbers?
I have
Nick
done
knows
some
more about that.
testing. I've done some testing, although not with their sensors, but it really depends on the duty cycle you run them. So for example, one of the details that didn't make it to this slide is that well, actually maybe it did. The tripwire LED, the tripwire LED consumption is pretty high, and that's why the tripwires are sequenced. So they can be pulsed at a very low duty cycle, but at a fairly high repetition rate, in order to have any object blocking them be detected without burning power there. So I think probably it would be safe to say, depending on your code and how often you turned on the Zigbee to report, 300 milliamps or whatever that the XB Pros take to transmit for long distances is probably the dominant power consumption when the thing turns on. I think it'd be safe to say that you could probably have an average power consumption of around 100 microamps or so. It really depends on your use cases, though. That's all under the control of the thing. Does that answer the question? Close enough. We're open for questions afterwards, too, so I'm, of course, very happy to talk about our beautiful baby.
And I was also, okay, so after that, I was a big part in the interfacing. So you can see on the left, that's the router, and the right is the microcontroller. And then there's the blue ports there in the middle, and that's where the communication occurred, TX and RX. So I just want to talk about one little problem that issue we came up with, or we encountered at least. And that was that when we wanted to communicate with the serial comm between the microcontroller and the router, since we're changing between low power mode and high power mode, when it was in low power mode, the comm becomes disabled. So when the incoming signal, you can see on the bottom right, comes in, what we decided to do was we took the RX and we split it, and so we put it also into the KBI. So with doing that, the actual signal triggered the KBI, because the KBI actually is still active. Sorry, I forgot to mention that. It's still active during low power mode. So that triggered it into high power mode, so the microcontroller is running with that. And with that, then the serial comm worked. And so that was one problem we came to, and allowed us to use the microcontroller for the rest of the sensors. So I think we're going to go into the tripwires now with
Actually,
Rob.
One thing I wanted to mention is, when I said that this microcontroller was showing its age, that's one of the things I meant. Unlike TI's MSP430 series and that sort of thing, this microcontroller is actually very limited in how it works in low power mode. So if you want to wake it up, receiving a serial character won't do it. It should, but it doesn't. There's only a few things that can wake it up, even from its lightest slumber, so to speak. And the keyboard interrupt, basically interrupt on pin value change or whatever, is one of them. The other is the real-time clock, and I'm not sure if there is any others, actually. So they had to do that. That was an interesting workaround that seemed to work.
All right, hey guys, I'm Robert, and my point, I worked on the tripwires with Cuddles over here, and pretty much I'm a hardware guy, so I'm not really too great with coding, but they did place the task on me to create a PWM, and for those of you who don't know, it's just something so we can generate our LED at a certain frequency. At the same time, like Nick mentioned earlier, we can save power with that duty cycle by running it. Ours is run at 50%, but you can change how long you want it to be high, in comparison to the period. So,
Actually, so to explain that comment, the system is using a television remote control receiver IC as something to strip off daylight offset and all the things that would scramble with your signal while being still off the shelf. But that means it needs a transmitted signal from the emitter LED at the frequency the TV remote control receiver needs to have it at, which I believe is 36 kilohertz. So the PWM hence comes from that.
As far as our tripwire sensor goes, as you can see, I have a little schematic up on the right, and it's just pretty much a simple LED circuit. You just use infrared, and we use the PWM, like I mentioned, to create that certain frequency for the sensor. And it's 36%. We also, out of our port, we weren't getting enough voltage, so we put a transistor in there just to up the voltage, and so we could get the right amperage, and the rain current, and it was like 15 milliamps. As far as our sensor goes, like Nick said, we use a sensor from a remote control. I mean, they're cheap. You can buy them pretty much anywhere. For I think ours were like $4 for like $2 or something, and for that, it was all powered off 3.3 volts, which is very convenient. And we just sent the output to the port where it was read by the microcontroller. This is our beginning stages of what our setup looked like. I mean, it's not much at first. You'll see it grew a little bit. But basically, we just had some infrared LEDs or infrared sensors, and we just sent the information back to the microcontroller. As soon as an interrupt would come, it'd go high, and that's the signal we'd usually read. Our current setup, though, it got a little more complicated. We decided, since we couldn't really have two microcontrollers on either side of the path, that it would just be too much wires everywhere. So we combined them, together and add a reflector. So it'd send the infrared light out, reflect back, and come to the control, or go back to the sensor, and we'd read the information from there. Also, our infrared sensor is very sensitive, we found out after changing around or messing around with the LED. And we hooked up a collimator to it, or pretty much as a ghetto collimator. We cut a pencil or a lead pencil in half, wrapped some electric tape around it, and just attached it on there just to kill some of the light coming in. At the last minute, we had this great idea. Like the other night, we just pulled an all-nighter, just trying to get this thing done. And we found this Nintendo, or this like original Nintendo, just laying around. And we also had infrared controllers with it. So it's like, oh, and we had the wires. We had the wires, like, and it's just so convenient because there's 5 wires running to the controller, and we just, for each of those wires, we just send a different like VCC to one wire, ground to one wire, the output and the input. And pretty much now our controller, we can just plug it right into the system as if it was a Nintendo controller plugging into a system, because we had the Nintendo inputs and we had the Nintendo outputs. So it's pretty awesome. Lastly, this is just a little picture of it. It shows what our final sensor looked like with the inside the case, and then we have a picture of it decased with the reflector right next to it. Also at the bottom, you can see the Nintendo inputs. Now I'm going to hand it over to Cuddles to talk more about more of the programming.
So I was tasked with the responsibility of counting how many people walked into an area with these sensors, and pretty much I just created a huge thing of code that would count people in an area. So what we did was we used the real-time interrupt, which I'm gonna explain in about a second, and the pulse width modulation that Rob just discussed. And pretty much this entire program works using flags. So, and there's a lot of them. And it's the code itself and the sensors are woken by the PIR sensor that Rob and Mike talked about earlier. So the real-time interrupt. What it is basically there's a free running clock inside the microcontroller. So what you can do is you can set the clock, and as you can see I did that in the code there. The last 3 lines, I set it to 128 milliseconds, which our goal was to set it to every 10th of a second, but that's close enough. So the microcontroller has a clock, and every 10th of a second it hits that 128 milliseconds. And in the code you have to acknowledge it so we can reset and interrupt again. So we use this to use pulse width modulation. So what happens is the interrupt happens and it turns on his hardware. So basically the sensors turn on and they gather all the information. So the sensor itself is there's 3 sensors connected to 3 pins on the controller, and the transmitters turn on and they send out a signal to the sensors. And the sensors read an active low when they receive the signal. But when a signal is not read, when someone's blocking it, it reads a high. So when that happens, it means someone's standing in front of it. So what I did was I used the code to say, okay, someone's standing in front of it. But what happened was, for some reason, when one person passed through, it read like 7 people. So I had to use a lot of flags to slow that down so it would read 1 person and filter it out.
This is equivalent to switch debouncing, actually. And in case someone has it in their mind, yes, we know that if 2 people go by at the same time, it'll only count 1. And if a bike goes by and your sensor's at the right height, you could think all kinds of funny stuff. So this is one of the reasons why a kind of probabilistic, filtery way of dealing with this data is essential, because it's really not very high quality data, despite your best attempts. High quality data is not really compatible with cheap sometimes. So, and if anyone has, if everyone knows what interrupt vectors and that sort of thing are, then please, just speak up. Don't want to speak what is already known.
Okay, so what I tried to do was, I tried to make code that no matter what happened with the way people walked into this thing, it would compute it and do it right. But I was having a little bit of trouble with that. So I set up 2 different situations. If 1 person walked through, it would hit the 3 sensors in order: the left sensor, the center sensor, and then the right sensor. So I developed code for that. And then I also developed code if multiple people were walking through at the same time. So if the left and right sensors were tripped, but the center one hasn't been tripped yet, that was a whole different situation. I set up another block of code for that. And the little picture at the bottom, I don't know. the reason all it worked was just a bunch of flags. I thought that was cool. You might not. That's fine. Okay, false positives. So say one person walks into one of the sensors and realized they forgot a book or something and ran back and went to get it. So now you have a sensor that read a 1 and it doesn't do anything with it. What we did was we put a counter inside of the code. So what happened was when a sensor was tripped, it would start this counting. And the way it works is every second it deletes all the data. So say a person trips it and then runs away. After a second, it'll delete all the data, so it's good. And it makes the algorithm a little bit more accurate. And some problems. Inaccurate readings. People can, it's not 100% like efficient, so you're not going to get a completely accurate count, but it'll be close enough to figure it out, like with the camera. And the code is a little bit rough. As I said before, the flags, they're everywhere. And if I showed you guys the code, you would lose all your hair in your teeth and you would cry. So that's, yeah. And my friend Steve over here coded another way to implement it using state machines. And it was good, I'm not gonna lie. But the code is my baby, so that's why I put that picture there too. People in my group got that, but nobody else will. That's also fine. And then, yeah, that's it for that slide. Conclusion. So RTI, we use that along with his PWM to count people that come in and out, and it saves a lot of power. How the code fits into the system? Well, basically, you don't want to look at a camera where you know no people are in the area. So say that a bunch of people walk into the area, you say, okay, let me check that out, just to make sure, if it's 3 in the morning, you want to look at that. So 3 in the morning, you look at the screen, and there's no people there, like doing anything. They're just walking. That's fine. So we count people for that reason. The problems are there, but the program will still do the job. And for anyone that plays World of Warcraft, word. But I was the only MMO player in this group, and everyone else plays like first-person shooters and strategy games.
Dude,
yeah.
I played WoW. I played WoW.
But I play more though. But yeah, some of you might play World of Warcraft. That's cool. Some of you probably hate it. That's cool too. But
He felt he was underrepresented, so.
yeah, exactly.
It's all right. We love you anyway.
All right, thanks, Nick. And okay, Alex is going to come up to you now and talk to you about his audio detection system.
Hi, how you guys doing? All right, enough about how big you are and to wow. But all right, so my thing is a scream and gunshot detection system, because obviously if you're screaming, something's wrong, unless there's a false positive, which I'll explain in a second, or there's gunshots, plat plat. That's not good. So so we're gonna. Really, guys? All right, so obviously my goal was to detect large changes in ambient sound, so just like people talking or something like that, like in the hallways, that's the normalized level. But if someone just says, "Hey you," there's going to be a spike there, so you'll see that. It's geared towards gunshots and screams. I mean, there's other sounds, but obviously things like firecrackers and stuff like that would set it off. Whereas the really nice shot spotter system in this fine city of University of Delaware, we're not here at my university, in Washington, D.C., that can detect the difference between a gunshot and a firecracker somehow, but one guy in 5 weeks can't quite build that system. So, possible problems. False positive, groups of freshmen and groups of girls, all right? So on these trails going around, you got to go to the party, you got to go to the frat party so you can get your hookup on and get your drink on and stuff like that. So the girls will drink in their room a little bit, and then they'll walk and hang out, and then they'll go to the party. Well, girls are they'll be screaming and saying things that girls say, and
dude, give us a demonstration.
I really won't. But so I think the next slide's a little comic I made just to illustrate this, how I want this to work. So you have that one girl represents a group of sorority girls, and the little black box represents the sensor. So they're just making some noise, and they're just moving close to the sensor, and they keep walking, and that's it. So the desired output is just a nice linear up and nice linear down. So, and I labeled the axis, even though that's pretty obvious, but I'm still in school, so professors take off for that stuff. So, but our next slide is actual danger. Now it's Sally Now, if Sally is walking back from the party a little buzzed and that same trail and there's a scary man behind a bush, and then all of a sudden he comes behind the bush or erases the bush, she's going to go, ah, and then that output would be like this. So I'll explain how I got the ambient sound to spike up like that and then gradually come back down. On the back end, the coding that we kind of didn't really have that much time to work with because we were focused more on getting the router to talk to the microcontroller, and there was only so many programmers, and I'm really not that good at that stuff, so I can like make the basic file for it, but not too good. So I did a lot of hardware mostly and a lot of collaboration. So initial build, I found this like nice clapper circuit online, and it's basically 3 op amps hooked up together with the microphone, and the first op amp is just a preamp, amplifies it with some gain. The next one's like an active filter, and the last one's a comparator circuit. And when one voltage is higher than the other, it makes this LED light up. I was like, oh, that's cool, because I have never taken a class in op amps or nonlinear circuits, not yet. So that's actually next semester. So hopefully I'll know more than I do now. And so, oh man, that's not in the right place. So with that kind of circuit, this is what would happen. It's just like random times, like, oh, bark, bark. Dog goes, and it's just that's loud. That would set it off, and you'd have to send a patrol car for that. Or we have lots of trains that come right through like the university, so that like random patch of stuff is like a train going by, so it'd just be a lot of noise. Well, after collaborating with Nick, he mentioned this thing called an envelope detector kind of filter thing, and that circuit would pass through a diode, which only lets a positive like signal through, and then the capacitor and the resistor kind of like let it out slowly. So woo-woo, cool oscilloscope outputs. The yellow is the audio input, so like that's like a hand clap or like a hey yo, what's up? And the nice blue one is the after it goes to the envelope. So you see how it peaks up and slowly lets it out. What the code does is it samples it beforehand, and then it will compare the previous value to the initial value, that value, and then when it goes up, it's like hey, new big value, and it makes interrupt. So skipping ahead a lot. And a lot of other things because we're running out of time. This is the end circuit. It's basically a preamp with the envelope thing after it. We could have gotten a lot more complicated and done a lot more things with it, obviously, but there just wasn't that much time / knowledge on my part. We actually talked about like an auto gain control thing where like the louder it gets, it turns the volume down, kind of normalizes the signal like in a whole like different, more complicated way that like with transistors and stuff, and I don't really know much about them other than they're cool, and among other things. And that's the output of this circuit. Not as nice. And I'm done because we're running out of time. Thank you so much. Keep it real.
So this is going to be kind of an abbreviated version, but I did the Python section. This was the pure programming part of the whole project, I guess, here. And the whole reason we wanted to actually be able to do this is I wanted to be able to size up the situation, pull down police reports off the internet, and be able to say, in this location at this time, your sensors need to be more sensitive because it's a high crime area at this time. Basically, here's the data flow for the entire system. You take the HTML from the page, goes to the Python HTML parser. Yeah, I know it's deprecated in 3.0, but it's okay. It puts the text into a CSV file, and then that gets dumped into a SQL database. Unfortunately, we ran into a little problem along the way, and little Bobby Tables there destroyed our entire thing. So, well, most of it. Also a reason why you should keep more backups. But from the MySQL database, you go to, we went to actually a KML file so we could plot everything onto Google Maps and get a visual representation, which is a lot easier to look at than just statistic graphs coming out and some stuff like that. Yeah, well, this is basically just a breakdown of everything. You start off with a table, you go there. I mean, you guys can see that. It's pretty easy to see, I guess. Anyways, we ran into some oddities, and I can urge you all not to use Dreamweaver and things in Microsoft Office that say save web page as. Makes
terrible HTML, just terrible. Okay, this is kind of like an overview of what the camo map looked like when we were done with it. It's about 11,000 crimes on there, but we had them kind of grouped in GPS coordinates on there. You can click on them, they blow up to like 1 million of them. It's like 5 years worth of data on there. And you can kind of see some trends and stuff when you zoom in. This is the pretty sweet user interface that I've been working on for months. No, I'm just kidding. I wrote it about 2 days ago one night with my friend Steve here. It's pretty sweet. It's written in ActionScript 3 Flex stuff. I never learned that before then. Uses PyAmp, very nice people in the IRC channel there at 4 a.m. That's pretty much it because I think I'm pretty much out of time at this point, and yeah. There you go. Here's Burke, and he's going to talk to you about computer tracking vision and stuff.
Sweet. So, what? Just go. Okay. So, you know, Steve was talking about the USB webcam, and well, we didn't really want to use that to, you know, just have someone sitting at a monitor surveilling stuff. So we wanted to add some intelligence. So, and that's called video analytics. Currently, there's no, you know, single best solution for this kind of thing. They all, you know, work differently in different lighting conditions and all this stuff, and they're all really expensive usually. Some open source systems do exist, but they're usually for scientific stuff like biology or physics, you know, like mapping how a ball, the trajectory of a ball or something like that for classrooms. What? Yeah, okay. And yeah, so like it's literally limited to very specific uses. Our requirements, we want it to be open source. We wanted to, you know, pretty much have adaptive background removal because the background will probably be changing if there's trees and the trees are blowing in the wind and varying lighting conditions. And we wanted to be able to get the output of objects, which would be, in this case, humans walking through an area. I ended up using Swiss Track, or tried to at least. It actually worked pretty well. But it's based on OpenCV. It has a really simple object tracking. Why do people keep talking? Very simple object tracking pipeline, and it used NMEA output for the positions of the objects on the like in the image. And it did that over TCP, so it was perfect for background integration because you could pipe it straight into the part that I'll talk about later. But for now, we also tried to get this running on the PS3 since there was a cell-optimized version of OpenCV. But that didn't pan out because no matter how many times I tried to build it, how many different operating systems, binary, compiled, whatever, there was always 1 or 2 OpenCV functions that SwissTrack needed that would not work. So results could track humans. It also tracked moving trees. There was a lot of stuff that actually ended up depending on the environment and you know, like contrast type stuff. It's all, you know, computers are stupid. And, but it did output to a very back-end friendly format. So false positives could possibly be minimized by the Bayesian classifier, which was the other part that I was working on, which was pretty simple. The idea was kind of a crime spam filter for this sensor network that we have. Inputs to the Bayesian filter are what the sensors are seeing. We just have to, you know, turn it into some kind of text format and throw it in there, and it figures out all the probability and all that stuff for us. And the output is the probability of some bad stuff going on. So the solution was format the sensor data into some kind of common textual format. So the objects on the camera would obviously be the NMEA coordinates, and the other stuff we can probably we just formatted the opcodes that Steve talked about a little, just in kind of an ASCII format, and also attach a relative time to the start of an event to them, and we throw it into Debacle, which I don't know, some of you might have seen an article on the internet about the developer of Debacle actually made a chess playing program out of what is basically a spam filter. And he actually, you know, hooked it into GNU Chess and could play chess against a spam filter, which is pretty cool. So the results, awesome idea and simple implementation. We can literally just take the output of the back end, pipe it straight into debacle and get the probability of something bad happening. Problems, it needs major tweaking there's a lot of stuff that I really won't get into, and it needs a lot of love. You have to teach it. And yeah, that's it.
What would be the processing power that would be required for this video analytics?
Okay, so pretty much it was running fine on my old MacBook Pro. That was for one video stream. If you get multiple, it might be beneficial to have a higher power system or maybe a cluster or a PS3 if you can get it working. But that's for another lecture, I guess. Oh yeah. All the processing is handled on the back end on some other computer sitting somewhere else. So it's all streamed to Swiss track.
And that, by the way, is part of the reason why you have the other sensors, because their job is to filter it down such that you don't have to burn all the power that's required, especially for a remote battery-powered system to be streaming video all the time, or worse, performing high-performance video processing to recognize stuff. It's all about filtering it down, that pyramid sort of.
Yep, so you don't just have to rely on one sensor. But, sweet.
So sorry we took so long. That was partially my fault. But the one point that we really liked about the PS3 that we're sad we didn't get working is that it works at what, 1/100th of the time?
Oh yeah, pretty much.
It takes 1/100th of order of magnitude, 1/100th of the time to process the stuff. So it could be really, really, really fast, and you could have multiple cameras ideally in real time if you got the PS3 version working.
It's also a lot cheaper.
And it's a lot cheaper. PS3 versus cluster computers, much different. So our conclusion is that routers combined with microcontrollers are going to be awesome, and that with the stuff that we'll be releasing soon on our website, you can go out, you can build yourself a cheap system, cost just over $100, and you can build yourself a basic security system, and then you can do all the stuff on the front end and the back end that you want. Basically, our implementation, when we boxed it up, we chose a PlayStation. Alex will show. So all that you saw today is housed inside this PlayStation, including the controller ports that Rob mentioned that can be interfaced to. So we thought that was a nice retro version. And yeah, basically that's it. We're the Circuit Breakers and Hack the Planet. Thanks for coming. Yeah, if anyone has questions, we'll take them outside.
Oh, okay, cool. Oh, really? Awesome. Yeah.
That's the microcontroller there sits Zigbee, and then this is the phone. You're using these interfaces also for the.
Sorry about that, guys. Thanks.
That's my point. Okay.
We did? Yeah. I thought we were supposed to finish at 4:50 and then we start at 5.
Like left and right.
Yeah.
We'll be ready in a second. Yeah, and we also have lots of information behind contact any of us. And you guys have
catch anybody with the we caught ourselves, but we didn't actually get the deploy.